Okay, good morning, everyone. Thanks for coming to this panel on sequestration of bio-CO2. So amongst the uses of the bio-CO2 coming out of the biomass plants, one of the uses is to put it underground. So we're going to go into a bit of detail of this method. It's known as BECCS, bioenergy with CCS, and it's one way to provide also so-called negative emissions. I'm Karim Rahmani, I'm co-founder of Carbon Impact. We are a developer of BECCS projects based in France. I'm be happy to moderate this panel along some colleagues. So I'll have Josh Dalby from Ricardo, a technology company, who will present an introduction about the technology by Ricardo to pyrolyze biomass in order to get energy, but then also CO2 that can be captured afterwards to do negative emissions. And I'll have a presentation afterwards by Patrick from EOSIS. So Patrick Portolano is a geological expert, so he will more go into the details of how we geologically sequester CO2. And then I'll give a brief introduction about BECCS in general and negative emissions to start this panel. So thanks for your attendance, and without further ado, I'll get started with a presentation on an overview of BECCS, and especially in Europe. Okay, so as I said, Carbon Impact is an independent developer of BECCS projects. It's a company that's been co-founded by myself and Alexander Schnell. We are power engineers, and we are working on retrofitting the existing biomass plants and biogas plants in order to make them able to do a geologic sequestration of CO2. And we're working on a portfolio of projects in Europe and in France. So maybe I'd like to start with something as a quiz, just to start to introduce the session. So how many of you are aware of the concentration of CO2 in the atmosphere today? Anyone has a guess? Yes, please. 420 something ppm. Correct, yes. Wow, you're sharp this morning. So actually, you can you can check the concentration of CO2 in the air on a website called co2.earth at any time. And what happens is that when CO2 is emitted in the atmosphere, it stays there, and the concentration, it's mixing in the atmosphere in the first 10 kilometers of the atmosphere, and then it's more or less mixing around the world. So in any place you will go, the CO2 concentration is more or less the same. And so currently the latest measurement is around 422 ppm. So it's changed a bit, but this is the range where we are reaching today. And actually this is measured in an observatory which is in Hawaii, in Mauna Loa. And there's a scientist in the 50s who started to measure the concentration of atmospheric CO2. And since then we have a record of the measurements like since the 50s, so we can track it. So the scientist was called Keeling, and he did a curve to show the evolution of concentration in the atmosphere. As I said, it started in the 50s. So who knows amongst you how was the concentration of CO2 in the atmosphere back in the 50s? So today it's 422 ppm. How much was it like in 1950? Anyone has an idea? Combien? 360. Actually, it was below 300. So if you look at the concentration of CO2 in the 60s, we were at around 320 ppm. So we went from 320 ppm to 420 ppm in a bit more than half a century. Okay, and actually, if you look back further in time, the concentration of CO2 in the atmosphere before the Industrial Revolution was around slightly below 300 ppm. So it means we are currently saturating the atmosphere with CO2, and this is basically the issue of climate change and global warming. It's basically the damages that we're creating in the atmosphere. We have some other greenhouse gases, but the damages we're creating in the atmosphere is directly related to this number, how many ppms are in the atmosphere. So, and we're continuing to raise this amount, and the damages are going to be more and more severe. So we need to stop this curve, basically to stop accumulating CO2 and using the atmosphere as a kind of landfill for CO2, which is here like a form of waste, of garbage. And so we're using the atmosphere as an open landfill, and this is why we need to basically decarbonize to stop the emissions. but we also will need probably at some point to remove and to reduce this concentration, because 420 ppm is already too high. So this is the role basically to explain simply the negative emissions. So when you look at what the science is saying, for example, the IPCC, you have these curves which say that we need to reach net zero. And net zero means we need to stop the accumulation of the carbon in CO2 form in the atmosphere. And to do this, we need to stop basically emitting fossil fuels and burning fossil fuels. On top of it, so this is the main part of the job, reduction of emissions. Like 20% of the roadmap to net zero is to reduce the emissions from current 40 billion tons per year of CO2 to as close as possible to zero. But then to be net zero, so to stop the accumulation of waste CO2 in the atmosphere, we need to compensate those residual emissions, which are estimated between 10 to 20%, so it's gigatons in total. We need to compensate them with carbon removal, basically, so taking CO2 out of the atmosphere. So this is the role of negative emissions. It's the blue, the dark blue part you see on the curve, which allows at the beginning to reduce the speed of accumulation of CO2, but then to get net zero, to stop the accumulation, and further down the line to start repairing the damage and to reduce the overall concentrations in the second half of the century. So how to do this? I mean, there's many ways to remove carbon from the atmosphere. When you look at the IPCC and again the science, it's a range of things. And they all have in common to take one molecule of CO2 in the air first, and at the end it's in a sink. And the sink can be either like biomass, like trees, forests, ecosystems. So this is one family of negative emission technologies or methods. And planting trees and forests is really the most, like today, the most used method to remove carbon from the atmosphere. But then you have a whole range of other ways to do it. And the outcome is always the same. So you take this molecule, you capture it some way. It can be by photosynthesis. It can be by technological methods. It can be by mineralization. And then you put it in a durable, more or less durable sink, which can be biomass, can be sequestration, geologic sequestration of CO2, can be mineralization in concrete or in durable products. So this is the whole thing that we called, it's a suite of methods, the carbon removals, and BECCS, the topic of today, sequestration of bio-CO2 is one of those methods. You can see it highlighted in red. And the purpose of BECCS is to use photosynthesis as a basis. So you have plants which capture CO2 from the atmosphere. And then they are used into a biomass plant. It can be biogas, it can be combustion of biomass, it can be fermentation. And this bio-CO2, which is normally goes back to the atmosphere, you capture it and you put it in a sink. Generally, it's geologic sequestration, but it can be also in materials, in concrete. And in this way, once you have done this whole process, you have removed one molecule of CO2 from the atmosphere. And of course, there are other methods, like you have plants that directly reduce and take CO2 out of the air. They are called DAC, for direct air capture. You can use the ocean, which is a big sink of CO2, and to change the chemistry of the ocean. So it's another method which is a bit less mature today. But however, BECCS is one of them, and this is the one we're going to discuss and focus on this morning. So if you look at Europe, for example, you have studies that shows what's the potential of removing CO2 from the atmosphere with this methodology. In general, you remember that the total number that needs to be performed in the world is in gigatons, so we're talking in billions of tons in 2050. And in Europe, we need to remove hundreds of millions of tons. This is what the EU is planning to do. And when you look at the potential of one of the methods of BECCS, we're talking about a couple 100 million tons per year. So when you look at the map of Europe, you have a number of biomass plants and biogas plants, and the 200 million tons is basically the CO2, the bio-CO2 that is emitted by those plants. So it's waste incineration plant, it's cogeneration plants, you have bioethanol plants, and all those plants and biogas and biomethane plants, they emit CO2 in their process, and this is what's creating this potential. If you zoom in France, it's more or less 10% of this amount. You have different studies, but it's in the range of 20 million tons of CO2 that can be removed in the atmosphere in France with this method. We already have in our national roadmap for decarbonization, the long-term roadmap called SNBC, the National Strategy for Low for carbon removal, 10 million of tons of BECCS planned in 2050, but the potential could be higher than that. So you have one first step, which when you are in those plants, you know, there are hundreds and thousands of biomass and biogas plants. The first step is to remove the CO2 from those, to capture the CO2 from those plants. And so I think Josh today will see one of those methods using pyrolysis that can be used to capture the CO2. But basically there are technologies today to take CO2 from a gas mix, from the off gas of biomethane plants, or from combustion flue gas from the biomass combustion plants, or from pyrolysis. So there are a suite of technologies to take the CO2 from that source and make it in a pure form. So then what you need to do is to transport it to a sequestration area, and then to put it in geologic sequestration. So in terms of transport, again, CO2 transport is a mature technology. You can liquefy generally for short distances CO2. And you put it, you need to compress it and to refrigerate it to, let's say 20 bars, minus 20 degrees. And then you can put it in a CO2 container. They are called isotainers. They are 20 tons containers that you can put on a truck. You could put on the isotainers on a barge. You can put them on a train. And then they are ready to travel for, hundreds or thousands of kilometers. And this is the type of transport that can be used for projects today. In the future, Europe is planning to build a CO2 pipeline infrastructure, also for hard-to-abate industries like cement and steel, and we'll have pipelines potentially of CO2 that allow transport in a gas or in a dense form, and this, for higher volumes of CO2, will be the future of CO2 infrastructure. But this will take, it's only the beginnings of this phase, and those pipelines will not be available before, let's say, 10 years, 15 years. And in between, there are methods to take the CO2 from the point of emission, from of the power plants or biogas plants that are on the map, to sequestration. So then the last question is where to put the CO2 in a durable way. And here also there are some projects that are taking place. Typically in the North Sea, you have areas like Norway or Denmark, which are starting projects where you can inject the CO2 back into geologic formations, so into rocks, porous rocks that are 1,000, 2,000 meters below ground. And once you have taken, you can take the CO2, inject it, and then if you do it in a proper way, and there is laws to regulate this CO2 storage in Europe, it's called the CCS directive. And once you have taken this, respected this directive, you can inject CO2 deep underground, and if done properly, it will stay basically in a permanent way. So today these projects are happening, and mostly in areas where we have exploration and production of hydrocarbons, like the North Sea. So the first projects operational today are in Norway, are in Denmark, and you have also in South Europe, in Ravenna, in Italy, by ENI, a project that has started operation end of last year. So you can see that all the bricks of, the BECCS value chain, emission of CO2, transport, sequestration are existing. So it's early days, it's not yet a massive optimized infrastructure, but it means that projects can be done today. And both Josh and Patrick will talk more in details about the different steps that can be used to make those happen in reality. And maybe the final step, the good question that can be asked is how to finance this negative emissions. Today, there's no penalty or no obligation to sequester biogenic CO2. It's considered, when the biomass is sustainable, it's considered as not a pollution, but as a circular carbon. So there's no, so the question is, what's the incentive to capture and sequester biogenic CO2? And today there is a voluntary market. So when you look at the latest figures from CDR.FYI, which is a source regarding carbon removal statistics, basically last year, so this is the number from 2024 third quarters, but yesterday the latest figures came out, and we had 8 million of purchases, 8 million tons of purchases of carbon removals in the world in 2024, starting from a basis of less than 1 million in 2022. So there's a high growth of carbon removal which is being purchased, and this is today driven by a voluntary market. So you have a list of the purchasers. These are big companies who have net zero goals and have understood that they need to basically compensate their residual emissions by carbon removals, and this is what's driving today the early stage projects that are happening. In the future, there will be potentially a regulation or compliance market for this. So typically the EU is already considering including carbon removal in potentially the ETS market. So there will be a recommendation by the Commission next year about that. So it means that in the next few years we will probably see the emergence of a compliance market that will allow to finance that type of method, which is needed to fight against climate change. And some countries are already started with financing and incentives also to start those. So basically it means that now we have the financing, we have the technology, we have all the bricks to make BECCS happen in Europe. So what's happening really? I will just end up with a couple of examples. Maybe on two extremes of the spectrum. So one of the leading projects in Europe is in Sweden. It's in Stockholm. There you have a large biomass plant which is feeding the heat network of the city of Stockholm using biomass, and it's emitting 800,000 tons of CO₂ every year of bio-CO₂. So now Stockholm Exergi, the owner of the plant, have decided a few years back to start to capture and sequester the bio-CO₂ from that plant, and they are reaching progressively milestones. So they haven't reached FID yet, but progressively they are filling the steps to make this project a reality, and it would be one of the biggest, if not the biggest, BECCS projects in the world once implemented. So they started a few years back by applying and getting some money from the innovation fund from Europe, basically. That takes the ETS money, the carbon market money, and put it into innovative products. So they get a first financing from the innovation fund. And then last year, actually, they completed, so they are selling the credits on both voluntary and regulated markets. So this is a good example because they have secured purchases of their carbon credits. So from both big buyers like Microsoft and Frontier, which is a club of buyers based in the US, but with a number of companies around the world. And so they have sold credits for a portion of the 800,000 tons per year to those voluntary buyers. And last week, actually, they also got another financing, a boost from the Swedish government, which allowed, awarded them. They put a reverse auction mechanism to buy BECCS projects. And they got a financing of almost 2 billion euros from the Swedish government to make this project happen. So potentially this project is close to FID, to final investment decision, and will start operation in the next 2 to 3 years. And it's an example of how you combine innovation financing from the EU, from governments, you combine voluntary market, you combine also systems of support by states, and then you can get projects that can take off. Maybe on another extreme of the end of the spectrum, a smaller project, and this is, I'm making just a few, ending this presentation, but with some plug about our company, Carbon Impact, but we're involved in a project in Switzerland to capture 4,000 tons of CO₂ in a biogas plant, which is based near Zurich, inland, and will transport the CO₂ to North Europe, potentially Denmark. And this project has achieved FID last year. There was a purchase of carbon credits by a Swiss entity called the Climate Sand Foundation that will allow it to happen. And hopefully the operations of this will start current 2026. Yeah, and finally, so based on this, we think the bio-CO₂ is from biogas plants is a useful way, or one of the uses of and the sources of BECCS. And so we're trying to replicate this project that took place in Switzerland by a similar project in France with the 3 biomethane plants in France, which emit 10,000 tons of CO₂, and we're currently selling the carbon credits to on the voluntary market to capture that CO₂ and sequester it underground where we can, basically. And this is today more in North Europe, but in the future we'll be able to sequester it in closer locations. So yeah, that's it from me. So thanks for your attention, and I will pass the mic to Josh to zoom in on an innovative technology for pyrolysis. Thank you very much. Maybe we can leave questions if you have at the end of the three presentations.
Great, thank you very much. Let me just see if I get my slides. No, I'm okay, thanks. Oh, great. Could we just go back one? Sorry, I think I pressed it. Yeah, perfect. Yeah, thank you everyone. So my name is Joshua Dalby. I'm Global Head of Research and Development at Ricardo. I'm going to talk to you about greenhouse gas removal through pyrolysis of waste biomass and flue gas carbon capture as well. So this is a technology that we've developed with some partners, and we've successfully demonstrated it just recently. Is that better? Thank you. So just very briefly about Ricardo, in case you haven't heard of us before, we're an engineering consultancy. We've been around for over 100 years, primarily in the transportation sector, but also moving into the energy sector as well. So we develop sustainable mobility and energy solutions for our customers. We're technology developers really, rather than producers, but we take them to market with our customers. There's about 3,000 of us worldwide in different regions, and we have about 2,500 live projects at any one time. So just to briefly set the scene, this project that I'm talking to you about is funded by the UK government. So why is the UK government focused on this? There's obviously a kind of glide path to try and reach net zero by 2050, and the UK is expecting to have a shortfall of about 40 megatons of CO₂. They are planning on putting in large-scale BECCS systems, as was described in the previous presentation, but they still think we need additional sequestration or capture in certain kinds. So a few years ago, they launched a net zero innovation portfolio and funded several projects to try and develop technologies in different areas. You can see that they're not kind of putting everything in one certain area. They're looking at technology developers in the UK to propose something that they think has value and take that forwards, both to help the UK out, but then also ideally to export that to other countries as well. Just very briefly, just in case you haven't been in the biochar room and biochar is new to you, I don't want to touch too much on it because I'm sure most of you are aware, but just to briefly introduce that biomass pyrolysis is one way of capturing carbon in biochar. So effectively, rather than combusting the biomass and releasing the CO₂, you leave some of it behind in a high carbon product. So it's typically 80–85% carbon. It's also very stable in that form as well. So it counts as a carbon dioxide removal technology. And it also has quite a lot of value as a product as well. So you get the kind of two streams of being able to sell it as typically a soil improver in other markets as well, but also being able to sell the carbon credit. And yeah, effectively it's a very stable form because you take all the hydrogen out. So kind of general research says it's stable in that form for several hundred years, maybe over 1,000 years. So it's there's quite a lot of interest at the moment in that, and the biochar market's expected to grow. So how does our technology fit in? So pyrolysis, I think, is very good and certainly has a place. There are challenges in scaling it up to the real, gigaton scale. So it typically is the kind of smaller energy industrial use that we're talking about here. It's very good. It typically captures about 50% of the carbon in the biochar. So because the process needs heat to work, you end up releasing some of the carbon as CO₂. And that goes back to atmosphere. So provided that you've got a sustainable source of biomass, and it's waste stream in our context, it's pretty good, but it would capture about 50% of the CO₂. What we've done, we think for the first time, is combine that pyrolysis process with a flue gas carbon capture system as well, a small scale one, so much smaller than the one in Stockholm that was showed above. So we're sort of operating at a few kilotons per annum, maybe up to 10, 20 or so, as opposed to the 800 that was mentioned before. But it's based on that larger scale technology, which is starting to be deployed in some places, but it's downsized. We're using our kind of automotive expertise to take cost out, make it affordable for operators of such plants. So the neat thing about this is that we can capture quite a lot of the CO₂ that's left in the flue gas. So we capture it in two forms. We've got the biochar coming out first, but then we can capture most of what's remaining in the flue gas at the end. So we can get 90, possibly up to 95% of the carbon captured, and the CO₂ in some cases that we're targeting would be utilised, but in other cases would be sequestered, depending on the end use. So we could see 90-95% of that carbon captured in total, which puts it in a comparable scenario with direct air capture that achieves similar kind of capture rate. The neat thing really is that the way that we've integrated the various elements of the system with the heat recovery and the power generation, it's quite complex, but it works really well. And what it means is that we actually have a net heat and power output as well. So as well as producing the biochar and capturing the CO2, we don't have to put energy into the system. It's self-sustaining, and we actually have energy and heat to export as well. So typically we find that actually that makes it quite an attractive commercial proposition. So we're not really reliant on the kind of carbon credit and removals market so much. That's a nice addition, but actually the co-products of the system, because the biochar has quite value, the CO2, if it's utilised and it's food grade, then that also has quite a lot of value as well. So the system has quite an attractive payback period in its own right. If this link works, there might be a video, but I don't know. We can try. Can you try clicking in the middle of the screen there? No. Next page. There's a link in the. Can you see there's a link? Always a gamble embedding videos. No. Well, you'll have to just come to our stand later on and see it. So sorry about that. But it's only a kind of minute and a half long, but it just helps set the scene in terms of the size and the scale of the plant, which we've designed, procured, installed, and now tested in the UK. So let me move on. I think. Could we do the next page? Okay, yeah, great. So I just wanted to kind of share with you then some of the kind of technical side, the challenges and the opportunities of integrating the systems that we have in this plant. We've been running various feedstock trials to see primarily on the quality of the biochar that's been produced. You can see at the bottom there, so going from a kind of premium wood chip to grass cuttings with a wood blend to slab wood, which is basically the bark and the exterior of the wood. Ash dieback, that's actually in the UK there's a fungal disease. I don't know if it's common in Europe, but the ash trees have to be cut down because they're dying basically. So there's quite a big program in the south of England. Those trees have to be cut down and disposed of. So we used that. We used also fruit farm plant residues, including the growing medium, which was coir. So quite a lot of green material, and then the coir, and then green waste, which is effectively kind of garden waste or hedge cuttings, that kind of thing. I haven't put specific numbers in here, but you can kind of see roughly what range the outcomes were. The only reason is some of them are a little bit variable, and with some further optimization of the combustion settings, we might be able to achieve different things. But you can also see a kind of indicative feedstock cost as well. With the downs being expensive and the ups being cheap, or in some cases you can actually be paid, you could have it as a revenue stream to take the waste, because if the local authority needs to dispose of it, then you can actually take that gate fee as a revenue stream. So there is a bit of a trade-off between the two. It's important to try and find the sweet spot, I would say, between the price of the feedstock and the quality of the biochar that you need to produce at the end. The higher grade biochar can typically retail for higher price because it can be used in other applications, and the lower grade might not have too much value. You can still sell it as a carbon removal, so you still have a revenue stream, but you might not be able to get the additional revenue from it. And then I didn't want to dwell on that too much, but then on the CO2 capture side, the kind of pros and cons of integrating CO2 capture with a pyrolysis-based system. So real positive here in the way that we've engineered the system is that because of the high levels of thermal integration, we can actually drive this CO2 system, which is based on temperature swing absorption technology. We can drive that with the waste heat that's left after our power generation unit. So it's effectively being driven for free. We're not kind of putting in any extra energy into that, which is really nice. Another benefit is the pyrolysis flue gas is typically done at low oxygen concentrations. So there's very limited oxygen in the flue gas itself. That works really well with a temperature swing absorption system because oxygen degrades the solvent, which then needs to be replaced every now and again. So it's quite a nice synergy of being on the back of a pyrolysis system as opposed to a gas system that runs very lean and has a lot of excess oxygen. So there's an improved kind of operating cost there. And the syngas combustion, I think if you're looking at kind of the feedstock variability side, I mentioned anaerobic digestion earlier. I think one of the challenges there with a biological process is the contamination of the feedstock and how that impacts the contaminants in the flue gas stream or the CO₂ stream that's being separated. The kind of positive of combusting that syngas is actually some of those contaminants get burned off and they don't cause you an issue. Whereas in the AD side, I understand that plastic contamination things causes an issue both in terms of what is emitted, but then also what's left behind as well. So there's some positives there. Challenges are lower combustion temperatures in pyrolysis mean that typically you have more particulates, so you need to have quite an efficient scrubber system to clean the flue gas before you try and separate the CO₂ out. The downside of that is if you're using a wet scrubber, you don't want to introduce too much water because then the water comes through into the solvent as well, so then you end up diluting the solvent and having to top it up and dispose of some. So you've got to find the right balance there. And clearly, obviously in some cases the contaminants that are in the feedstock lead to pollutants in the flue gas stream, which can go into the CO₂ as well. So there is a little bit of a trade-off also in terms of how much purification you need to achieve to get to the right standard versus the feedstock cost. So that's it. So there was a bit of technical detail there towards the end, but very happy to answer questions here, or also if you want to come to our stand later on, I'll be at J29, which is just along there in the biochar area. So and actually there's there's an augmented reality version of the plant, so you can actually look at that on a tablet and kind of zoom in and see what everything looks like. So you're welcome to